Hi, everybody. Welcome back to, I believe, lesson 16 of Intro to Physics. We're still working through some more energy example problems and how all of these different types of energy work together, how we can use these different types of energy to solve these sorts of problems. And again, these problems are very typical of ones that you might see in Physics 1. So hopefully as we go through these examples, you'll start to see those patterns that were mentioned in the video yesterday. And sorry, not yesterday, today's Monday, on Thursday. And once you get a hang of these patterns, then you'll probably find that these energy problems are actually much simpler to solve than some of these other types of problems that we've been doing previously. So for example, this example that we're starting out with, example 5, skateboarding. Now, if you look at the problem, a skateboarder coasts 8 meters per second on flat ground, then encounters a long ramp. How high does she get on that ramp if she just coasts? Well, reading that scenario and looking at the picture, you might notice that there seems to be a crucial detail that is missing. And that would be the angle, right? Nowhere are we given the angle or a way to figure out the angle that this skateboard ramp is on. And if we were doing forces, just forces, then that would be a problem. We'd need the angle in order to kind of analyze the forces that are happening here. Same thing with projectile motion. If we were to use our sort of projectile motion equations, we would need to know the angle. But when we're dealing with energy, we don't. The angle doesn't really factor into um, our problems very much. So um, this is one problem where energy approach is actually much simpler. So let's go ahead and take a look. All right. So as you saw in the examples last week, when we're dealing with energy, remember energy and work are related to each other through the work energy theorem. So the work energy theorem tells us that the amount of work done on an object or done by an object is equal to the change in kinetic energy. And now we've kind of we've gone beyond just kinetic energy into also gravitational potential energy. And so now we're not just dealing with the change in kinetic energy, but we're dealing with the total change in the energy is equal to the amount of work done by other things. So that's where we're going to start off with in all of these examples today. The change in energy equals the work due to other sources. In this case, we're not explicitly told that there's friction. We also don't really have a way to calculate things with friction or air resistance. So we're going to assume that this is a simple case where we're ignoring friction. And so the work due to other sources, friction, for example, is 0. And the way that we calculate the change in energy is the final energy minus the initial energy. So since that equals 0, then our initial energy equals the final energy. And in this case, energy is conserved. We talked about that on Thursday. Energy being conserved means that in a system, the total amount of energy cannot be created or destroyed. It will stay the same the whole time. It might transfer between different objects or different types of energy, but the total amount of energy is constant, right? So our initial amount of energy equals our final amount of energy. So since we've been talking so far about kinetic energy and gravitational potential energy, those are the two that we're really looking at here. And if we think about it, that makes sense, right? Kinetic energy deals with objects that are moving. So anytime you have motion, you have kinetic energy. And the skateboarder is coasting, so he's moving, so he has kinetic energy. Now, gravitational potential energy occurs anytime that an object is off the ground or at a different height than your than your coordinate system, than your 0 point. So again, remember, you can set your 0 point to be wherever's most convenient to you. So in this case, I just set it to be the ground, right? So when our skateboarder is off the ground, then he will have some amount of gravitational potential energy. So thinking through that then, right? At first, our skateboarder is on the ground, so he has no gravitational potential energy, no kind of potential to fall to the ground if he's already sitting on the ground. And since we're interested in how high the skateboarder gets on the ramp, well, once she's gotten to that maximum height, she will not continue to move farther up, right? So at that moment, when she's at the maximum height, her kinetic energy is 0 because her velocity is momentarily 0. And remember, kinetic energy is 1/2 mv squared. So once her speed reaches 0, then her kinetic energy will be 0 as well. So kinetic energy at first is 1/2 mv initial squared. And then that gravitational potential energy at the end is mass times g times that final height. And in this drawing, we can see the final height is labeled YF, so Y final. Well, as you can see, we have the mass on both sides of the equation, and she keeps the same mass the whole time, so we can cancel out those two masses. And now we're solving for YF, right? So we know her initial speed here is 8 meters per second. So 1/2 times 8 meters per second squared divided by g, so divided by 9.8 meters per second squared, gives us a final height of 3.27 meters. And again, that's taken from the ground being our 0 point. So that would be 3.27 meters above the ground, not necessarily along the ramp. Okay. Example 6, friction doing work. So if I shove a box across a mostly smooth floor at 2 meters per second, and then let it go and wait for it to slow down and stop, if we're given here this coefficient of kinetic friction to be 0.15, that means we're dealing with a fairly slippery surface, right? Remember, coefficient of friction, the closer it is to 0, the more slippery the surface is. So we're told that it's a fairly slippery surface, both in words, right? Mostly smooth floor, and in numbers, the coefficient being fairly close to 0. So thinking through this, are there any external or other forces that are acting on this box after I let it go? And then will that provide work on the system? So yes, there is an outside, external, other force that's acting on this box, right? It's not just gravity or the normal force or my push. There's also the force of friction. And does that provide work on the system? Yes, it does, right? That's going to change the amount of energy that this box has. So will this work be positive or negative? We know it's not 0, so it's either positive or negative. Is there any change in gravitational potential energy to deal with in this scenario? And is there any change in kinetic energy to deal with? Well, let's think about what friction does in any system, right? Friction opposes motion. And so it's acting to slow down the motion of this box, right? So if we're starting with a faster speed, and then due to friction, we end up at a slower speed, that means the work that it's doing on this system is negative. It's slowing down the object, doing negative work, taking energy out of the system by transforming it into, heat or that sort of thing. So negative work. because of friction. Is there any change in gravitational potential energy? Well, no, this box stays on the floor the whole time. So if we set the floor to be our 0 point in our coordinate system, then nice, easy numbers there to deal with. There's no height above the floor. There continues to be no height above the floor. So there's no change in gravitational potential energy. Is there change in kinetic energy? Well, yes, the box is slowing down because of friction. So let's take a look at our scenario now that we've thought through some of those initial questions. Right, here's our box on the floor. Initially, it's moving at 2 meters per second, and the coefficient of kinetic friction between these two surfaces is 0.15. So we want to know how far it will slide before it stops. We're taking that floor to be our 0 point. Again, just to make the math simpler. So just like last time, we're going to start out with our work energy theorem. So our change in energy equals the work done by other sources. And in this case, that's the work due to friction. So our change in energy is the final minus the initial. And now thinking about work done by friction, remember work, as we talked about last week, is the force times the displacement times the angle between the two of those. Right, so we have our force of friction times the displacement that it moves, which we don't know, times the angle between those two. Okay. So again, there's no gravitational potential energy due to where we've set up our coordinate system. So we're not going to even bother writing that down into our energy final or energy initial term, right? We just have kinetic energy, so that final energy minus initial energy becomes final kinetic energy minus initial kinetic energy. The force of friction, we talked about, what, 2 weeks ago now, I guess? The force of friction is mu, that coefficient, times the normal force. And then again, we have times the displacement times the cosine of the angle between them. So our final kinetic energy is 0 because we're waiting for it to slow down and stop. So remember, once it's stopped, it's no longer moving. So its speed is 0, so its kinetic energy is 0. And since friction acts to oppose motion, that means the force of friction is pointed back to the left and its displacement is to the right. So that's a full 180 degrees between those two. Okay. So the cosine of 180 degrees is -1. And that's how we get this negative out front here. This negative comes from the fact that it's 0 minus kinetic energy, so negative kinetic energy initial. Since our box is sitting on the floor, not on an angle, that means that the normal force is equal to the force of gravity, right? Those two forces are balanced. So where we see this normal force, we plug in mass times g, right? That formula for force of gravity. And since we have a negative on both sides of the equation, we can just pop that out, ignore that, cancel it on both sides. Right, so 1/2 mv squared equals coefficient times mass times g times displacement. We can see there's a mass on both sides of the equation, so that factors out, which is good because we weren't given the mass. And so taking that equation and solving it for just the displacement gives us the V initial squared divided by 2 mu g. Fortunately, we have all of those numbers. So we can just plug them into our equation, plug them into our calculator. we get a displacement of 1.36 meters, which seems fairly reasonable. 2 meters per second, you're pushing it at a fairly swift pace, right? If you picture a meter stick, or if you're American, picture a yardstick, that's fairly close to the same thing. Then that distance is being, two of those are being covered every second, right? So this is a um, fairly fast speed to push a box at. Which means when you stop pushing it on a fairly slippery surface, it will continue to move for a little while. And a distance of 1.36 meters seems reasonable, much more reasonable than like 136. So remember to think through, evaluate your answers, see if they make sense or are in the right ballpark before you put that little box around them and move on. All right, example 7, the Atwood machine revisited again. So I wanted to include this example because, again, Atwood machines are things that are very, very common in Physics 1. You'll see them in Physics 1 lab. There's just a lot that happens with these Atwood machines. And there's a lot that happens in this problem. It can be a very complicated problem. So my recommendation to you is to stay organized. Take it one step at a time. Don't try to jump ahead too much. Just do it bit by bit and you'll work your way through. Here we go. A box of gravel with a mass of 130 kilograms slides on a rough surface. Ooh, friction. Being pulled by a bucket of concrete, mass of 65 kilograms. Find the speed of the box of gravel after it has moved 2 meters. The system starts at rest. Okay, so again, a lot going on here. Let's take a look. So at rest means its initial velocity is 0 for both objects, right? Since these two objects are connected by a string that we're assuming is a perfect string, it's not going to stretch or snap or anything like that. That means if one of the boxes is not moving, then the other one cannot be moving either, right? And at the end, the speed at which one of them is moving is going to be the same as the speed at which the other one is moving. Not necessarily in the same direction, right, but the same magnitude. They're both going to move the same distance. So if this box of gravel travels 2 meters, that means the concrete bucket is also traveling 2 meters. Again, it's the same rope. It is not stretchy. Okay, so those things are actually really helpful to keep in mind as we go through this. So since we have two objects, we need to look at both of them. They both have energy that's being contributed to this system. So just like previously, our change in energy equals the work due to other sources, other things. So here we have the total energy from the box plus the total energy from the bucket. And that equals the work due to friction. Okay, so I tried to have everything in this problem separated by color. Hopefully that's not too confusing for you. But everything pertaining to this box of gravel is going to be in orange. And everything pertaining to specifically the bucket of concrete is going to be red. So initially, well, I guess not initially, but just in general, we're going to be looking at the kinetic energy and the gravitational potential energy for both objects, right? Because that's the sum of those two things equals our total energy. Well, this box, since it's sliding across the table, if we choose the table to be our 0 point, then that can make the math pretty simple. You could choose another point to be your 0 point if you'd like to. But either way, no matter what your 0 point is, this box of gravel is moving horizontally. So there's no change in the height at all, which means there's no change in the gravitational potential energy. So we can automatically ignore that for the box of gravel. So if we're thinking as well that the tabletop is our 0 point, I guess we wouldn't necessarily have to choose the tabletop as our 0 point, but let's say we chose the bucket where the bucket is initially as our 0 point. This bucket of concrete is falling downward by 2 meters, right? Because that box of gravel is moving sideways by 2 meters. So that change in the height for this bucket of concrete is going to be negative 2 meters, no matter where our 0 point is. Okay, so taking our delta terms and breaking them down into what they really mean, right? The change in kinetic energy for our first object is its final minus initial. Again, change in kinetic energy for a second is final minus initial. Change in gravitational potential for our second object is final minus initial. And all of that, again, equals the work due to friction. So since our system starts from rest, that means anytime we see an initial kinetic energy, we can cross that out. That's automatically 0. And if we set the starting height of our concrete bucket to be our 0 point, then we can take that out of our equation as well, because the initial height being 0 means that its initial gravitational potential energy is 0. Okay, so remembering those things greatly simplifies our problem. Plugging in our equations for kinetic energy and gravitational potential energy. So again, remember that this final velocity of the first object equals the final velocity of the second object because they're connected to each other. So I'm just going to call that final velocity. It's the same for both, so let's just use one variable. The work done by friction, remember we saw this in the previous example, is this mu, the coefficient, times the normal force, times the displacement, times the cosine of the angle between the force and the displacement, which for friction is 180 degrees. All right, we know our masses, so we can plug those in. We know G is 9.8 meters per second squared. We know this concrete bucket is falling down a distance of 2 meters, so -2 is our final height. And so once we do that, you can see that, well, we're also plugging in our values for the work due to friction, right? So our coefficient is 0.4. We can see that in the picture, right? The normal force is the mass times gravity. And this is the mass of the box of gravel because that's the one that's sitting on a table being supported by a normal force. Times the displacement of 2 meters times the cosine of times the cosine of 180 degrees, which is -1. All right, so once we plug those things into our calculator, group together our final velocity terms and simplify as much as we can, we get a final velocity of 1.62 meters per second. Okay. Whew. So as you can see, our expressions got very long and then they got kind of condensed again, and then that's just the nature of physics. But it really does help to stay organized. So um, I don't know, maybe while you're working on homework problems and that sort of thing, you could do a similar strategy, right, where you have a different color for each different object, and that will kind of help you keep them straight in your head. That helps me. If that doesn't help you, then don't do that. All right. So I want you to give these couple problems a try really quickly, just to kind of test your conceptual understanding of energy and conservation of energy. Here's a roller coaster. We're going to assume that this cart starts at 2 meters per second. Right, so that's its initial speed. Put the locations in order of the lowest speed to the highest speed. So where is it moving the fastest? Where is it moving the slowest? And how can we order these points appropriately? I'm going to give you a minute to think through this, and then we'll come back together and talk about it. All right. So remembering conservation of energy, right, and our sort of our relationship between these different types of energy. Remember, energy is not created or destroyed, but it can transform from one kind to another, right? So from kinetic to potential and potential to kinetic, it can transform between those. So when we're thinking through which place has the highest speed versus the lowest speed, right? That's asking about the kinetic energy, because kinetic energy is the one that deals with speed. So the place that it has the lowest speed is the place where it has the lowest kinetic energy. Due to conservation of energy, that's going to be the place where it has the highest potential energy. And it has all of this potential to fall and go faster. But right now, with all of that potential energy, it's moving very slowly. So, really, we can think about this not in terms of where is it moving the fastest, but where is it the highest? Um, Sometimes that is easier to analyze in a scenario than um, where is it moving the fastest. So if we think about where it has the highest potential to the lowest potential energy, then we are also answering the question of where it has the lowest kinetic energy to the highest kinetic energy. And so, of course, we can see there at point A, it's the highest off the ground, so it has the most potential energy there. The next highest point is D. The next highest point is B. The next highest point is C, and the lowest point is E. So this B is our correct answer. And if you've ever been on a roller coaster before, I know they're not like everybody's favorite thing to do. But if you can visualize what it would feel like to be on this roller coaster, then you might be able to actually kind of, from your own experience, feel where you would be moving the fastest and the slowest in this roller coaster. Okay, so related question, put these locations in order of lowest potential energy to highest potential energy. Well, we just did that, right? Lowest potential energy would be the place where it's the lowest off the ground, right? So this would be point E, then point C, then point B, then D, then A. So this is kind of the opposite, actually exactly the opposite of the question that we just answered. Okay, so now let's put some numbers to this and actually do this as an example. Right, if this cart starts at a speed of 2 meters per second, it has a mass of 350 kilograms. We're asked to find the speed at each point and the normal force at point B. Okay, so since we're going to be dealing with forces, I went ahead and reminded you of the equation for Newton's second law. So the net force equals the mass times the acceleration. But since we're asking for the normal force at point B, and point B is the middle of a loop, we're dealing with a special kind of acceleration here that I haven't talked to you guys about yet, and that's the centripetal acceleration. So we'll talk more about centripetal acceleration and centripetal versus centrifugal force probably next week. But I went ahead and wrote the equation there for you so you can see it. The centripetal acceleration equals velocity squared divided by the radius of the circle. Okay, so finding the speed at each point. Well, we're given the speed at A, it's 2 meters per second. Woo, got one done. We know it's going to be moving the next fastest at D. So let's take a look at point D then. Okay, so initially we're starting at a height of 25 meters at point A. And so this cart at point D is finishing at a height of 16 meters. So 12 meters is the height of the loop, and then point D is 4 meters above the highest point of the loop. So 16 meters above the ground is our final height, or our height at point D. Again, starting with this same energy work relation that we have been doing so far, we're not considering friction in this case. So the work done by other things is 0, which means we're just dealing with conservation of energy. So its initial energy equals its final energy. Now, initially, we are dealing with a kinetic energy because it's moving, and a gravitational potential energy because it's above the ground or above our 0 point. And same thing at point D, right? It's above our 0 point and it's moving. So we have both types of energy at each of those locations. So let's go ahead and substitute our equations for kinetic energy and gravitational potential energy. We have a mass in each term. So technically, we did not even need to know the mass of this roller coaster to be able to know how fast it's going. But I went ahead and left it in there just in case that's something that you might not notice as you go through these problems. You can still plug in the mass and it will still give you the right answer. So 1/2 times mass times initial speed squared plus its mass times g times its initial height equals 1/2 times the mass times its final speed squared, which we don't know, plus mass times g times final height. So the only thing that we don't know is that final speed, or the speed at point D. So once we type all those things in our calculator and solve for that final speed, we get 13.4 meters per second. That's considerably faster than it was at the beginning. But it could make sense because it is faster, which is what we expected. So let's hold off on assuming that we're correct or incorrect until we've gone through and calculated the speed at some of these other points. Then we'll have a better reference to compare to. So point B is our next highest, and following a very similar process, right? I'm still going to use point A as our initial point, just because we can be sure of those starting conditions. We were given the initial height, we were given the initial speed at point A, so I'm going to keep that as our reference point. But now the height of B is 12 meters. So again, same setup as before. We're not considering friction. So our final energy equals initial energy. At both of those points, it's still moving. It's still above the ground. So we have both of those types of energy at each location. Now all we have left to do is plug in really just this final height. That's the only thing that's changing here in this equation from point D to point B is that final height. And so once we plug that into our calculator, we can see this final velocity is 16.1 meters per second. Okay, so that's faster than 13.4 meters per second, which we would expect. So far, so good. Now looking at point C, because that's our next highest. Here we're only 3 meters off the ground. But again, we're following the exact same procedure. Now the only difference between point C and point B and point D is that final height. So now we just plug in 3 instead of 12 or 16. And so our final speed at point C is 20.9 meters per second. Okay, again, bigger than point B, which is bigger than point D, which is bigger than point A. So far, it's looking reasonable. Lastly, we need the speed at point E. Okay, this time, point E is right level with the ground. That is our 0 point. So its final height is 0. Okay, which means when we plug in our numbers for our final height, this whole chunk right here is going to disappear because anything times 0 is 0. And so doing that, we get a final speed at point E of 22.2 meters per second, which again is faster than any of the others. So that seems plausible. Okay. So hopefully you can see that by just setting up this problem once correctly, we were able to very easily figure out the same thing at each different location. So take your time, set up these problems carefully, and then you'll be able to kind of recognize some of those shortcuts. Now we're not done with the problem yet though, because you were still asked to find the normal force at point B. Okay, so we found the velocity or the speed at point B to be 16.1 meters per second. We're just going to assume that our calculation was correct because it seemed plausible. All right, so here's our cart. At point B, we know it has the force of gravity pulling down towards the center of the Earth. But in this case, the normal force is sort of weird because this cart is not sitting on top of the loop at point B. It's sitting underneath the loop at point B. So our normal force is kind of pushing it down towards the center of this circle. Right? If you think about it, if you think about what your body wants to do as it goes around a loop, it wants to kind of fly outward. And so that inertia, that tendency of your body to want to continue its motion and fly outward, has to be balanced by the track holding it in. And so that's why this normal force is pointed in towards the center of the circle. Okay, we'll talk more about circular motion next week. But this equation is the one that I gave you at the beginning, right? Our centripetal acceleration is velocity squared divided by the radius of the circle. Okay, so we know that the total height of the loop is 12 meters, which means that the radius of the loop is 6 meters. We found the speed at that location to be 16.1 meters per second. We square that. We get a centripetal acceleration of 43.2 meters per second squared. Using Newton's second law, the net force equals the mass times the acceleration. Well, now we're specifically dealing with circular motion, so the circular motion net force equals mass times our centripetal acceleration. Our net force, since the normal force and the force of gravity are pointed in the same direction, we're adding them together. So our normal force then equals this ma minus our force of gravity, mg. All right, mass is 350 kilograms. That acceleration we just found to be 43.2 meters per second squared. G is 9.8 meters per second squared. So that gives us a normal force of 11,690 newtons, which is a very big force. Um, but I mean, it needs to be a big force to keep you from flying out of the loop, which is what the tendency would be because of inertia. Okay. So do you guys have any questions about these couple of examples that we did together today? Tomorrow we're going to add in some additional sources of energy that we haven't talked about so far, like springs. We'll see how that can affect um, these conservation of energy problems. Um, but any questions from you guys? I know we finished actually 15 minutes early. Um, so I'm an open book if you have any questions. If not, then I hope you guys have a great rest of your day, and I will see you all tomorrow when we talk about springs.